Oh, excellent. All right. So part B, separable ODEs. Yeah. So let's do a few more word problems. First one, B.1, mixing problem. Yeah. Right. Problem number 4. Look at the question. Yeah. The tank. Yeah. Yeah. So here, we want to so look at this tank. Yeah. Mixture. Yeah. Yeah. Water. Yeah. Yeah. So let's look at the question. The tank contains 1,000 gallons of water, in which initially 100 pounds of salt is dissolved. 1,000 gallons of water, put a 100 pounds of salt in it, yeah, and mix it. Yeah. All right? Yeah. That's the initial condition. All right? Yeah. It will change later. Initial condition. Brine runs in at a rate. Inflow part. Inflow. Yeah. At the rate 10 gallons per minute. Each gallon contains 5 pounds of dissolved salt. Yeah, not water. Yeah, some salt in it. Okay. Yeah. All right. That's the inflow part. The mixture in the tank is kept uniform by stirring. Yeah. Yeah. Stirring. Okay. Yeah. We assume the mixture is in a perfect way. Yeah. The density is uniform everywhere in the tank. Yeah. Assumption. Brine runs out at the same rate, 10 gallons per minute. Yeah. Inflow, outflow, the rate is the same, so the whole system is balanced, right? Yeah. Always balanced. Yeah. All right. Find the amount of salt in the tank at any time. Function, our y function. You need to calculate the y function. Your y function represents the amount of salt in the tank. And the initial value for that function is given. Amount of salt, 100 pounds. Initial value of y function. After that, when time changes, that amount also changes. That amount also changes. Okay? Yeah. What is that function? That's the question. All right. Yeah. Let's do some analysis. Our target function, y function, amount of salt, y of t. Yeah. Amount of salt in the tank. Yeah. Then, initial condition, y of 0 equals 100 pounds. Yeah. All right. Then, modeling, we need to apply some law, right? Physical law. Yeah. Modeling. Yeah. What law? Yeah. There must be some law. Right? Yeah. Balance law. Yeah. This whole system is balanced. Yeah. So there is a physical law to describe the balancing relationship for the whole system. Yeah. The balance law gives us this equation. Rate of change, y prime of t. Rate of change of the amount of salt in the tank equals inflow, outflow. Okay, inflow. Inflow, you add salt amount, right? Yeah. When the brine flows in, you add certain amount of salt. Add certain amount of salt. Outflow, you lose certain amount of salt, right? Yeah. You need to take the difference. So you have certain gain, amount of salt gain, inflow. Then loss, you need to remove outflow, that part. This is the balanced law. Rate of change, y prime, equals the difference of inflow and outflow rate. Yeah, rate. Both sides, you can, if you look at this equation, both sides represent rate concept, right? Rate of change, that's rate, right? Inflow rate minus outflow rate, also rate. So we represent rate in two different ways, according to this Balance law. All right, next, to solve this equation, we need to figure out what is the inflow rate, what is the outflow rate. Then we have an equation. Yeah. All right. Yeah. Salt inflow rate, yeah. Amount of salt per minute, inflow per minute. Per minute. Yeah. Rate, we need to take a appropriate time unit. Here we use minute as the time unit. Per minute, 1 minute. In 1 minute, how much salt flows in? Okay, all right. Yeah. In 1 minute, 10 gallons of brine flows in. That contains 5 pounds. 5 pounds per, yeah, because we look at the salt part, right? Yeah, salt part. Yeah. Yeah. Oh, each gallon, each gallon 5 pounds. We have 10 gallons, so multiply. Yeah, yeah. Sorry, I didn't. Yeah, each gallon. We have 10 gallons. So in 1 minute, 10 gallon flows in. 10 gallon contains 50 pounds of salt. That's the in rate. This is the in rate. 50 pounds per minute. Inflow rate. Outflow rate, mixed. Yeah. So you need to figure out the density, right? Yeah. What is the density in the tank? Or the amount of, think about, the amount of salt in 1,000 gallons of mixture. Total, 1,000. Certain amount of salt, Y of t, right? Y of t is the amount of salt in the tank. But you have total 1,000 gallons. Then, how many gallons of mixture flows out in 1 minute? 1 minute, 10 gallons. So from 1,000 gallons, you take 10 of 1,000 gallons, right? Yeah, because total 1,000 gallons in 1 minute, you only take 10 gallons. Look at that. Salt outflow rate, yeah. The amount of salt per minute outflow. Per minute, 1 minute, 10 gallons. 10 of 1,000 gallons. Look at that. 10 of 1,000 gallons. 1,000 gallon corresponds to Y of T salt, right? Y of T pound of salt. Yeah. Yeah. But you only take 10 out of 1,000. 10 out of, is that 0.01? Yeah. So this 0.01 comes from 10 over 1,000. Yes. Because in 1 minute, you take 10 gallons from 1,000 gallons, right? Yeah. Yeah. So you get 0.01. Yeah. This Y amount is in the 1,000 gallon of tank. So you only take small portion of it. You only take 0.01 of Y. Outflow. Flows out. Remove it. Okay, that's the outflow. Yeah. Then you have the, based on this analysis step, you have the final equation. Yeah, this is the final equation. Y prime equals 50, inflow number, yeah, constant, yeah, minus 0.01 Y, outflow. Expression, amount of salt, outflow, per minute, yeah, rate, per minute. Yeah. Yeah. That's our modeling function, modeling equation, ODE. So we need to solve this ODE. Yeah. Next, step number 3, solve this equation. And it, you know, separable ODEs. Separable ODEs. Yeah. All right, so let's continue. Yeah. Solution part. Yeah. Initial, yeah, we have the initial condition. Y of 0 equals 100. Yeah. We need to determine the Y function. Yeah. Here, now, our old experience, yeah, because here the equation is different from our decay model equation. Completely different. So here we need to use a different method. Yeah. Develop a new tool. Yeah. All right. So let us do observation. Yeah. Look at this. So for this equation, yeah, you only see Y, right? Y prime, left-hand side. Right-hand side, another expression of Y. You only see Y. Yeah. But Y is a function of T. Y is a function of T. That T variable T is hidden. You do not see T in this equation. It is hidden. Hidden way. All right. So then, we want to find a special way to find a solution. The variable T does not appear in the equation, but it is useful, right? Yeah. Variable T is useful. Although you cannot see it, but you cannot ignore it. You have to use it. In order to use it, you have to reveal it. Make it visible. Reveal it. All right? Yeah. Some of you can solve, yeah, because you have the background, solve basic ODEs. Yeah. How to take advantage of this property? Yeah. Formula transformation. Here. Do some formula transformation. All right. Here. We use a different expression for Y prime. Y prime derivative, we can also write dy over dt, right? Another expression, equivalent expression. But this new expression has some advantage over that y prime expression in this situation because t is visible. In new expression, dy over dt, we make t visible because t is useful. We cannot ignore t. So we want to bring it out, t. Yeah. So we should use the new expression, dy over dt here. Yeah. So now we write this new equation, dy over dt. Okay? Yeah. Yeah. This new equation, we have more room for manipulation. Yeah. More room than our old way. Old way, we're limited. A lot of things we cannot do in the old equation. But this new equation, yeah, we can do more. Yeah. Yeah. So we change a view. Yeah. After the view change, we can do more on this newer version. All right. Importance here, from the derivative view, y prime, derivative view. So we only use the derivative concept here. Yeah. Then we change the view. This is dy over dt. Actually, we use a slightly different view. Although the whole thing, the ratio is also derivative, but dy and dt, they are differentials. So here, we use the differential concept. Differential concept also important in calculus. Now, a lot of things we need to use the differential concept. All right. Now, the benefit of this new view, because the differential will allow us to write y prime in two separable differentials, dy and dt. Two separable differentials. That's the advantage. That's the main reason we want to take the differential view. Yeah. Many of you, based on my experience, previous 2 semesters, many students are not familiar with the differential concept. Yeah, because when I talk about differential, I saw so many students feel puzzling, intrigue. What's the differential? Not feel very comfortable. So I will give you some background information about this differential. Because this concept is very important. You need to pick it up. Calculus concept. All right. Why the separate way is useful here? Separable ODE. So that's the technique we want to use to solve this equation. All right. Separable way. More room to manipulate the terms. Now, old way, t hidden. T hidden. If you cannot see t, you cannot do anything on t, right? No way you can do anything on t. But the new way, so you make t visible. Now you can do manipulation on t. Okay? You have y terms, you have t terms. Now we want to separate y and t. Left-hand side, y terms. Right-hand side, t terms. Separable. We do not put them at the same side. Here, both y and t appear at the same side. That's not convenient. Mixed way. But this technique, we want to separate these two parts. All right. With differential, because dy, dt, that differential. Some quantity, some, So the meaning of differential, actually it's a very abstract concept. So why large number of students do not feel comfortable using differentials? Because what's the concrete differentials? It's hard to imagine the concrete differentials, because it's very abstract. Differential concept is very abstract. So that's the reason many students, they try to avoid differentials. We should not avoid differential. We need to use differentials. All right, here. So we separate. dy dt can be separate because they're differentials. Otherwise, people, how can you write it this way, right? So is it illegal? Is it legal, right? Because some people may feel it's illegal. Actually, if you use the differential view, it is illegal. All right. Critical formula transformation. This time, we put all the y terms at the left-hand side, all the t terms at the right side. That's the true separable form. Completely separable. Then we take integral. We can find a solution. All right. So one variable. One variable, we have the confidence to handle one variable expressions. All right. How to remove the differentials? We know by integration. Take integration both sides. Then the inverse operation of differential, integral, both sides. Do calculation, simple calculation, these two expressions, not very hard, right? Here, in order to save a few minutes, so I put it in the further explanation number 1. So here I do not need to, so many of you can do it, but if not, then remember in the first class I explained some basic calculation. I moved to, after class, I record some video called further explanation 1, 2, 3. Because each class we may lose about 20 minutes, right? Break time and, attendance check time. We may lose some minutes. So I try to use that part of the time to do further explanation. Question?
So is that one of the YouTube videos then?
Yes.
Further explanation?
Yes. All right. So I will do it this way. So for today's class, our first class, I do not need to do that. So for today's class, we have our 2 normal lectures. First half, 1 video. Second half, 1 video. Right? Then below these 2 videos, the bottom part, optional, further explanation part. Number 1, number 2, number 3, each one I attach a YouTube video. So click. But I make sure the total number of minutes less than or equal to 120 minutes. The upper bound is 120 minutes. All right. So let's move. So assume we can solve it. Here I give you the final result. The solution. After this part, you get the final answer of that. All right. So we complete this example. All right. Then let's move to next example. B.2, structure of separable ODEs. solve separable ODE. So here the general method to solve separable ODE. Yeah, actually, we can see it easily. Yeah. All right. So this is the implicit form. That is the explicit form. Yeah. Yeah. All right. First order ODE. Yeah. And all right. So for the implicit form, so actually not equivalent. Yeah. Implicit form, most of the time you may not be able to convert it to explicit form. Yeah. 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 So this one easy, so we can convert it to explicit form easily. Yeah. But for some relatively hard one, so look at this one. A little harder. How do you write y prime equals some function explicitly, right? You cannot, because this y prime is inside sine function. So this implicit form cannot be converted to explicit form. Yeah. Yeah. All right. And then it's hard to solve. It's hard to solve. Many differential equations, ODEs, many of them we cannot solve. Yeah. 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 Like this one, how can you solve it? How can you solve? Yeah, so here, actually, what do you mean solve it, right? What do you mean solving an ODE? Yeah. Find a solution. Yeah. Find solution, what kind of solution? What is a solution? What is the form of a solution? Yeah, equation. So we call it analytic solution. If you can write a formula, so you expect some certain formula, right? So if you can find a formula, we call it it's an analytic solution. Yeah, because you have an analytic form. But sometimes, many times, the equation may not have the analytic solution. No such solutions. No way to find analytic solutions. Then we have another way to do the solution, numerical solution. Numeric. So you don't have formula, but we can generate numerical values to represent solution, numerical solutions. Okay, yeah. So this semester I try to squeeze some time to show you the numeric solution idea. Okay, yeah. All right, yeah. So but here let me just go a little faster. Yeah, yeah. Try to solve explicit form. Yeah. Initial value. Yeah. Yeah. So, strategy. Yeah. So here. Yeah. For easier case to harder cases. Yeah. Derivatives is constant proportional to the function. Yeah. That's very easy. Yeah. The easier case. Yeah. So we separable. A little harder. Yeah. Still easy. Yeah. Still pretty easy. Yeah. So we have this kind of form. Separable. Left hand side. Only y functions. Yeah. The expression only has y terms. Right hand side, another variable. Yeah. So separable ODEs. Yeah. Another simple case. Yeah. We can solve. Yeah. Yeah. Take integral. Yeah. Both sides. Yeah. All right. Yeah. So sorry. Yeah. So that's the what we are doing at this point. Yeah. Okay? All right. Yeah. Next, I want to do another problem number 5. Yeah. Okay. All right. Yeah. Heating an office building. Yeah. Another real world application problem. Heating, air conditioning. Yeah. Heating the building, the temperature. Yeah. All right. Let's look at the question. Yeah. So in this room, yeah, we want to measure the temperature in this room. Yeah. Heating, air conditioning, Yeah. All right. Suppose that in winter, the daytime temperature in a certain office building is maintained at 70 degrees Fahrenheit. The heating is shut off at 10 p.m. office. 10 p.m. Yeah. Turn off. Okay. Shut off. Yeah. All right. And then turn on again at 6 a.m. Yeah. All right. On a certain day, the temperature inside the building at 2 a.m. was found to be 65 degree F. Yeah. All right. And the outside temperature was 50 degree at 10 p.m. Outside, inside, different temperature. Inside you have air conditioning. Outside, different temperature, 50 degree at 10 p.m. And it had dropped it to 40 degree at 6 a.m. Outside temperature. Question: what was the temperature inside the building when the heat was turned on at 6 a.m.? Question. All right? Yeah? Yeah. Another interesting question. Yeah. First, we need to understand the question. Yeah. We need to comprehend the given information. Yeah. So if you just read the description here, it may not be easy to get the whole idea, right? Yeah. How do you comprehend all the given information? Not that easy, right? Yeah. Here, let me use the diagram because we want to represent the given data visually. Using the diagram, the visual way, we can see the picture better. Oh, sorry. Oh. Yeah. Yes. Oh, broken. Yeah. Hmm. Yes, broken. Let me try. Oh. Oh. No. Oh. Yeah, really broken. Yeah. But I have a backup one. Yeah. Hmm. 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 That. Oh, here, the backup one. Yeah. All right. Yeah. All right. The diagram here. I use this line segment to represent the line time period from 10 a.m. to 10 p.m. to 6 a.m. The line segment. Okay. Yeah. So we want to get a better understanding. Then, that point, 10 a.m. 10 p.m. Before that point, the room temperature is constant 70 degrees. All right. Another point, 6 a.m. Yeah. The room temperature, because turn on, right? The air conditioner after that point, turn on, there it takes some time to get 70 degrees, right? Yeah. So I put ... but that part is not important. Yeah. Yeah. All right. Then another point in the middle, 2 a.m., right in the middle between these 2 points, 65 degrees. But all these temperatures are inside the room. Inside the room. All right? Yeah. So I draw this circle, oval, represent the room. Okay? Outside this circle, that's the outside temperature. Inside the circle, that's the room temperature. All right? Yeah. So outside the room, there are 2 temperatures. 50 degree at the 10 p.m., but outside the circle, outside the room. Okay? 40 degree outside the room at 6 a.m. Yeah? So that's the visual representation of the data. Yeah? So we can see the question better. Yeah? All right? Yeah. And we need to find the temperature at 6 a.m. Yeah. Room temperature, inside. Room temperature at 6 a.m. That's the goal. Okay? All right. Yeah. Analysis. Yeah. Here. Modeling. Yeah. To do the modeling, we need to apply some physical law. Appropriate physical law related to the temperature of the system. Yeah. This whole system. Yeah. Yeah. So that's the Newton's law of cooling. Newton's law of cooling. Yeah. Okay? Yeah. What's that? Yeah. The time rate of change of temperature, capital T, temperature. Capital T is a function of time, little t time. So time rate of change, derivative of the temperature, capital T, of a body B. Body. Here, our office is the body, right? Yeah. Office, body. Yeah. B is proportional to the difference between T, room temperature, T means the room temperature, okay? And the temperature of the surrounding medium outside, okay? Outside surrounding medium, yeah. Outside environment, there is a temperature, okay? Yeah. So the difference between T and the temperature of the surrounding medium, that's the Newton's law of cooling. Okay? All right. So based on that, this is the equation. Rate of change derivative, dt, d capital T over d little t, equals proportion, some constant, k, times the difference, T minus T sub A surrounding temperature. Okay? T sub A, surrounding temperature. But in this Newton's law of cooling, that surrounding temperature, that is a constant. Yeah. Newton's original, that law, surrounding temperature, it uses the constant. Yeah, but our current question, surrounding temperature, yeah, at 10 p.m. 50, at 6 a.m. 40, it's not a constant, right? It's not constant. It changes. Yeah. But in this situation, yeah, it happens in the real world situation. In this one, we try our best to approximate the condition. Approximate. We try to find a relatively fair way to approximate. Yeah. So what's that? What's that? The way is we estimate TA. Because in this equation, we have to use constant T sub A here. And what is the best choice of T sub A? So we make an estimate. Yeah. A simple estimate is we just take average of those two temperatures. 50 and 40 add up, divided by 2, 45. Yeah, because we need to use one constant number. So we feel the best one for us to use here, 45 degrees. Okay? All right. Yeah. Now we are ready. Yeah. But here, this is an assumption. Okay? Yeah. When we solve real world problems in this kind of situation, yeah, it's very common. Yeah, because nothing is perfect. Nothing is perfect in the real world situations. So under that situation, you can make your own assumption. But you want to make the most reasonable assumption. Not some wild assumption. Yeah. Very reasonable. Yeah, here, the average of these two numbers, very good assumption. Yeah. All right. Yeah. Then you can write this explicit equation, and you know how to solve it, right? Yeah. Separable, you know how to solve it. Initial condition, you have the initial condition. T of 0 equals 70. Yeah. 10 p.m., we treat that point as the 0 time. Little t equals 0. Yeah, that's our starting time. Okay, T0. Yeah. T of 0, the 10 p.m., 70. Yeah. And we need to find T of 4. Oh, sorry, this is given. T of 4 is given. Yeah. And we need to find T of 8, right? Yeah. Because 6 a.m., that's T of 8. To solve that, let me put it in the further explanation number 2. Okay? In that way, you can see we complete another two problems. Yeah. 2 problems from part A, 2 problems from part B. So we did 4 problems today. Yeah. Try to improve, yeah. Yeah. So but 2 further explanations, yeah, after the class. Okay, all right. Yeah, that's it. Yeah, let you go. Yeah.